We ended our lecture on Friday talking about the Sapir-Whorf hypothesis. And this was reflecting one of the sides in the debate about how language and cognition are related. And so now we're going to talk about the other side that takes the view that language and cognition are actually separate from one another. So a proposal made by a philosopher named Jerry Fodor, he made quite a different argument about the relationship of language in comparison to other aspects of cognition. And so Fodor argued that some cognitive processes, particularly our perception and language, are modular. And so let's look at what it means for a process to be a module, at least in the view of Fodor. So when we say that language is modular, it means that first, this is a process that is domain specific. So it operates specifically with certain kinds of input, but it won't engage with other kinds of input. And so with regard to language, for example, Fodor argued that sentence parsing or cognitively dividing up different parts of sentences involves processes that are really specific to what it takes to divide words and phrases into their respective components in terms of constructing a sentence and also understanding them. And these processes, because they're meant only for this linguistically focused parsing or division, they're really of little use for any other cognitive task. And modularity of a process, it also implies that it is what's called an informationally encapsulated process. That's a mouthful. But essentially, this is the idea that language operates independent of any other information that's available, any other beliefs that are available to a processing system. And so another way of explaining this is to say that an informationally encapsulated process operates relatively independently of other processes. And so the modularity hypothesis then argues that certain perceptual and language-based processes are modules. And these processes are thought to be really set apart or independent from other cognitive processes, such as memory, attention, thinking, and problem solving. These elements of cognition are thought to be non-modular. That is, they're interdependent. They can interact with one another rather than just kind of staying in their own lane and doing their own sort of thing. And so another idea that comes along with this is that language is really this sort of special, set apart, and independent cognitive process. So let's look at what might be some evidence for this modularity hypothesis. So there was an experiment by a researcher by the name of Swinney that gives us some evidence for this idea of modularity. So in this study, Swinney presented people with spoken passages. These were passages that were read out loud to them. And so some of these passages contained ambiguous words, words that were more vague or just broad in their meaning. They weren't really specific and clear. And so some of these experimental participants heard passages that had more ambiguous or unclear wording in it. whereas other participants heard other passages that were still about the same topic, but used a lot more clear or unambiguous language. And in each case of uh, um, like I was saying, the unambiguous versions, the clear versions, they again were similar in meaning to the more ambiguous words. So essentially, you have two different conditions where a text passage is read aloud to participants. They're similar in topic. They're similar in the general meaning behind the words. But in terms of their clarity, that's where there is a difference. And so while people were engaged in hearing these spoken passages, they were also given a visual lexical decision task. So in this task, they were given a string of letters, and then they were asked to decide really fast, as quickly as they could, whether that string of letters formed a word, an actual word in English or not. And so Swinney found that when people were presented with an ambiguous word, when they came across a word that wasn't very clear, even when it was presented in the context of a passage in which you had other context clues that you could use to maybe sort of help you figure out the meaning of the word. When people reported that that what happened was all of the possible meanings that could be associated with these more broad, vague words really just kind of all came to mind really quickly. They were really triggered for just a fraction of a second. And this triggering of these word meanings, these appeared to be automatic and reflexive and completely independent of whatever other cognitive processes might have been going on at the same time. So, for example, maybe some of the problem solving abilities that were needed for the lexical decision task. Those processes were still functioning while at the same time there was very specific, very nuanced language processing that was also happening. And so here we have the evidence that there is this informational encapsulation, that there is this sort of this independence between language function and other cognitive functions. And so in addition to empirical research, in addition to Swinney, there's more than just one experiment that's been done. But we can also look at neuropsychology as another source of evidence that lends some support to the modularity hypothesis. And so the fact that we process complex language information with really just remarkable speed is really an understatement. There's a study by Kaplan in 1994 that reported that people typically recognize spoken words after about 125 milliseconds. So that's about 1/8 of a second in which people are able to recognize spoken words. Essentially, this means that we are understanding words while they're still being spoken. So you are understanding what I'm saying before I have even finished fully forming the word. And also, in addition to this, he found that normal word production that was estimated over a number of different studies it requires us to do a very extensive search through our lexicon, through our mental dictionary. Generally, we're running searches throughout about 20,000 items. And we're able to conduct these studies, we're able to conduct these searches extremely quickly. So, obviously, the brain architecture to support this really rapid and complex cognitive processing, it has to be sophisticated in some sort of a way. And so neuropsychologists have been trying to understand what the underlying brain structures that are involved with language are, as well as where they're located and how they operate in the brain. So this interest in localizing or really pinpointing where language function in the brain takes place, it dates back to at least the 1800s. There's a French doctor who was really interested in anthropology, ethnography, and his name was Pierre Paul Broca. And so he was reading a paper that was being presented at a meeting in Paris. And the paper reported on a patient who had been nicknamed Tan because he had lost the ability to speak any other words except for tan. So if you try to have a conversation with this gentleman, he would still be using the same sort of vocal intonation and inflections, but that we normally would, but the only word that came out of him was tan. So he would say things like tan tan, tan tan, tan tan, tan tan tan, tan 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 tan. And so this obviously was a very startling case, and it makes sense why someone would have written up a case study about him. And after his death, very shortly after his death, his brain was examined during the autopsy, and he was found to have a lesion or an area of damage in the left frontal lobe of his brain. And this area of damage you can see here on the PowerPoint slide is in this red region here. And this area of the brain came to be known as Broca's area. And subsequently, there were several other patients who were reported in these academic and medical circles who had really similar difficulties in speaking to the so-called TAN, and who were also found to have damage in the same brain region as well. And then about 13 years later, there's a German neurologist by the name of Karl Wernicke, and he identified another brain area that if it was damaged, often as a result of a stroke, it left patients with really, really hard time comprehending language, but they didn't have any problem producing language. And then so, not surprisingly, this area has come to be called Wernicke's area. So both of these language disorders were called aphasia. And as they were continued to be studied, the nuances and the differences between them started to become more pronounced. I have a video by a rehabilitation psychologist who does work with people who have had strokes, traumatic brain injury, things like that. And she does a really great job describing what an aphasia is, and then also just really simply describing the difference between Broca's area-related aphasia and Wernicke's area-related aphasia.
Aphasia is a very, it literally just means lack of language. So after a brain injury, whether it be traumatic or whether it be from a stroke, that affects traditionally the left side of the brain, which is where most of us, where our language center is. And there can be expressive aphasia, so an inability to express your words. So it's almost like tip of the tongue syndrome times 1,000. So the person's like, oh, I need and it's like you play charades a little bit with the individual. Like they know what they want to say and they just can't get it out. You can have receptive aphasia, which is your inability to understand what someone's asking you. So you might speak fluently, but you're not making a whole lot of sense because you're not understanding. So someone with receptive aphasia might sound like, for you said you did, you think I said you sure. It's fluent, those were all real words, but they don't have any meaning. A lot of times after stroke, particularly to the left side of the brain, or severe brain injuries that affect the left side of the brain, you can see individuals with, either global aphasia or mixed receptive and expressive. And I find, that can be terrifying to a family member and an individual if you don't understand what's going on. So I just think explaining to the person, because with expressive aphasia, it can just be so frustrating. Just imagine constantly having tip of the tongue syndrome.
So, as she was explaining in that video, let me go back to our slide. As she was explaining in that video, what's called expressive aphasia, or also commonly called Broca's aphasia, this is when somebody's language comprehension is still intact. They're still able to understand what you're saying. However, like she was saying, they have difficulty producing language. And with receptive aphasia or Wernicke's aphasia, we see an opposite pattern. So here with Wernicke's aphasia, the person has a really hard time understanding what is being said to them, but they're still able to produce language. Although, as she noted in the video, it's generally not always the most sensical. It's really rather nonsensical language that is often produced. But at least in comparison to people who might have expressive or Broca's aphasia, they are at least able to get words out. And so there have been other kinds of aphasias that have been reported, but the Broca's aphasias and the Wernicke's aphasias have really led researchers to notice an interesting sort of generalization or pattern about about the aphasic patients that they're studying. And they found that usually the area of damage to the brain was in the left side, not the right side. And so then this led to the idea that the two cerebral hemispheres, the two halves of the brain, play different roles and have different sorts of functions. And the term for this specialization of function between the two hemispheres is called lateralization. So briefly, it appears that in most people, the left cerebral hemisphere is associated with the ability to produce and comprehend language, which makes sense because both Broca's area and Wernicke's area are on the left side of the brain. And the right hemisphere is often associated with the ability to process complex spatial relationships and visual spatial information. And so evidence for this lateralization began with clinical observations, going all the way back to the time of Broca, of patients with aphasia. And as we've gotten more advanced with imaging and also neurosurgical techniques, we've also had evidence come from those areas as well. Specifically, there's a test that's used with people who are possible candidates for brain surgery to treat epilepsy. These are typically people who the anti-seizure medication that they've been taking hasn't been working, and they're really experiencing very severe disruptions to their life. And so this is what's called a WADA test. And so we're going to watch a short video about a woman who has epilepsy and is undergoing this evaluation, which includes a number of tests, one of them being a WADA test, to see if she's a good candidate for this seizure-reducing surgery.
It sounds drastic, removing part of the brain to stop seizures.
But doctors at the Nebraska Medical Center perform epilepsy surgery about 4 times a month.
KETV News Watch 7's Julie Cornell is following a young woman through the fascinating process. Julie?
It's risky, it's scary, but for an Omaha mom with uncontrolled seizures, brain surgery seems to be the only option.
You give a 5? Yeah!
On the surface, life is good.
Hi!
Meg Boozing is a nurse, married, with a new baby.
I don't know how I would be surviving all this without him, because he keeps me going, keeps me coming home, from coming home and crawling into a ball.
For her, I just want some relief for her.
Relief from seizures that have taunted this young woman for 10 years. A car crash when she was a teen had a lasting impact on her brain. She has 30-second partial seizures where she can't move or respond. Meg is undergoing intense testing to see if she's a candidate for brain surgery, trying to stop the seizures.
It's extremely high level, very high stakes type work that we do.
Dr. Deepak Madhavan is an epilepsy specialist at the Nebraska Medical Center, guiding a growing number of epilepsy surgeries in Omaha.
Head trauma is a very common cause of epilepsy.
He's ordered this unique scan on Meg to monitor her brain's electrical activity. This machine, called MEG for short, is just one of 15 in the country, mapping precise parts of her brain that control language and movement.
Okay, Megan, we're going to start here just a second. I want you to keep your head really still for me.
She reads words, even taps her fingers, with those responses lighting up the scans. On another day, another challenging test.
It's the fear of the unknown when you have seizures.
This time, Meg's in the operating room. Dr. Madhavan explains.
Basically what we're doing is we're simulating a stroke or a large amount of brain pathology for about 15 minutes or so.
Using a chemical to paralyze half of Meg's brain.
So you see he's working his way up.
They want to see how Meg would function without the damaged hemisphere causing her seizures. Watch as the medicine takes effect and her language shuts down.
9, 10, 11, 12, 12.
A little teeny bit more.
It was scary going into it, not knowing how it was going to feel.
What's your name?
So that's the half of the brain.
Madhavan will use this information to plot a brain map for surgery.
So far what we know is that the left side of her brain is definitely her language center, and so we have to be careful when we do surgery to be sensitive to that because her seizures come from the left side.
Seizures that Meg says are stealing her life.
Just a sense of loss of control is one of the hardest parts, because everybody wants to feel like they're in control of their lives.
Control that could come with brain surgery.
If the surgery was successful, I think it would empower me to do so many new things.
Well, through testing.
So the second procedure that she underwent, where she temporarily lost her language abilities, that is an example of a WADA test. And so these WADA tests have helped us with generally having an understanding of, there it is, of generally having an understanding of where the language center of the brain is. But as you heard in the video, a lot of tests can also be used to determine with some certainty where the language center of the brain is. And that's because not all people have language in the left hemisphere. So there are some differences depending on if you're right-handed or left-handed. So in people who are right-handed, about 96% of those people will have their language-related abilities lateralized to the left side of the brain, whereas the remaining 4% of those who are right-handed will actually have their language in the right hemisphere. So they'll have sort of this switching of hemispheric lateralization. And then people who are left-handed, they still show this this pattern of the majority of them having language in the left hemisphere. But actually about 15% of them have language in the right hemisphere, and then another 15% have language in actually both of their hemispheres, interestingly enough. So in addition to this evidence that we've talked about so far, we can also look at neuroimaging, such as CT and PET scans, to study language functioning in people who have aphasia, as well as people who don't have aphasia. And if you remember back towards the beginning of our course, when we were talking about the different kinds of neuroimaging, a CT scan is essentially giving you a snapshot of the structure of the brain. So as you can see here on this image, without the orange part, that would just be just the regular CT scan. It's just this still image in time that just shows the general layout and structure of the brain. Now, if you add a PET element to that, this is when there are safe radioactive chemicals that are injected into the person's bloodstream. And what a PET scan allows us to do is then to look at the activity of the brain. And so here we have on the slide, we have a combination of both the structure of the brain given to us by the CT scan, as well as a sense of the areas of activity that are shown to us by the PET scan. So you can see the orange areas are lighting up during a particular task. You can see that there's the Broca's area and the Wernicke's area that are both lighting up. So presumably this person is undergoing some sort of language-related test while they are in the scanner. And so there have been some studies that have continued to support this idea of language lateralization, as well as kind of this modularity hypothesis that Fodor presented, this idea that language is something that's unique and on its own and different from many other cognitive processes. So in a study using both CT scans and PET scans, Kempler et al. In 1990, they studied 3 patients who had a particular kind of aphasia. It's called slowly progressive aphasia. And they were able to look at what the brain volume of these folks looked like, as well as their brain metabolism. And so they found that these people who had this kind of aphasia were showing less brain volume. That is, they had actually less brain tissue, and they also had less brain activity. That is, the brain, the metabolism was slower. The brain wasn't firing as much in the left hemisphere. And so there's another study, it's kind of considered a classic study now in the neuroimaging aphasia world, but it was conducted by Peterson et al. In 1988. And it was examining the processing of people's production of single words, production and comprehension of single words using PET scans. And so in this study, participants were presented with single words. It was either in writing or read off to them. And they were asked to either make no response at all, to read off written words that they were seeing, or to produce a word that was related to the word that was given to them. And so the results of this study showed that different areas of the brain were activated for different tasks. So in this study, the people who just simply were viewing words on a screen, it was found that they had activation of the inner left hemisphere in the occipital lobe. So if you remember back to when we kind of broadly and generally talked about the neuroanatomy of the brain, the occipital lobes are in the very back of the brain, and this is specialized for visual information. But when the task was simply to just listen to the words that researchers were reading off to them, participants showed increased activity in both of the temporal lobes. These are the lobes of the brain that are close to the ears, and they have to do with auditory processing. And so another important finding, aside from just sort of this pattern for visually encountering words and a different pattern for having words read off to participants, is the fact that the brain areas in the study, in terms of their activation, there wasn't an overlap in this pattern. And so in other words, the area of the brain that had been activated with the written words is separate from the area that became activated when the words were heard. And so when presented with a visual word and asked to pronounce it, these participants showed activation in both of their hemispheres, but in an area of the brain that is involved in motor behaviors. Interestingly enough, the PET scans, when this happened, didn't show elevated levels of activity in either Wernicke's or Broca's. However, when participants were asked to generate a word in response to another word, there were these other areas of the brain that had previously been sort of quiet, so to speak, that became active. And so we started to see with this study, and also many studies that following it that have replicated it, that there seem to be these different patterns and this different involvement of different brain structures based on the demands of the task that a person is engaged with. So there's a difference between just hearing information passively, not having to make a response, versus seeing information versus having to make a response, etc. However, other research has clouded this really neat picture that we've been kind of tracking up to this point. So it's not as black and white though, because not all people who have damage to the Broca's area of their brain, not all of them develop Broca's aphasia, and also vice versa. Just because you have Broca's aphasia does not guarantee with 100% certainty that your Broca's area has been damaged. Also, not all of the people who have Broca's aphasia show the same degree of language impairment. Many of them show an inability to process more subtle nuances of language. So it's not always the case that somebody's going to have this very apparent and disruptive expressive aphasia. And the story is similarly complicated with Wernicke's aphasia as well. So going back to that Kaplan study, so he concluded that the localization of specific language processing, tying that to particular brain regions, it actually isn't as straightforward as we'd like to think. And so one idea that he put forth is that, well, maybe language processes don't necessarily have a specific location in the brain. So perhaps it's not the case that you know, being able to produce language quote unquote lives in the Broca's area, and understanding language lives in Wernicke's area. But rather, our language abilities may be distributed across several brain regions in the form of neural networks. And so this can account for why just because somebody might have a similar pattern of damage, they don't have the same sort of difficulties, because there could be location differences between person to person. But perhaps it's better to think of and understand it as rather that there are pathways that are involved that connect the frontal, parietal, temporal lobes. If it's visual information that's being processed, potentially the occipital lobes as well. And so this might help us understand why in certain cases, when people have had maybe smaller lesions or smaller areas of damage in an area, they might not fully lose or fully have their let's say expressive abilities, for example, fully knocked out. So if they let's say they were to have Wernicke's aphasia, it might be the case that you know a small area of damage might have affected that, or it might have taken a lot more damage to that area to actually produce that. But overall, oh, I've jumped ahead too fast. But overall, it appears that the neuropsychological findings and the neuroimaging findings that we've reviewed, they do lend some support to Fodor's modularity hypothesis of language development. However, as is often the case, when we have to go from just talking about theory and then studying how it plays out in real life, it's often a lot more complex and nuanced than the theory states. So even though these sorts of theories like the modularity hypothesis are helpful for us in terms of thinking in more sort of concrete and simplified terms so that we can better understand it, often, as is the case in the real world, it seems like it's more complicated than that. So we're going to end our chapter on language development by just briefly talking about bilingualism. So being able to speak two languages, or perhaps more than that if somebody's multilingual. And so here, it seems that there could be potentially differences between people who speak one language. These are called monolinguals, bilinguals, people who speak multiple languages or multilinguals. So, sorry, my computer just froze. Okay, so anyway, so the reason why we're talking about this is because knowing more than just one language is very common. So it's estimated that more than half of the people in the world are at least somewhat bilingual, if not proficient with more than two languages. And so some people live in countries where at least two languages are really commonly used, and sort of gone back and forth with. So for instance, Canada, Belgium, Vietnam. Other countries are bilingual because their home language is not the language that is used for school and for business, for the workplace. So for example, Nigerians, they must learn Hausa as well as their own specific tribal language. And there are also some people who are bilingual just as the outcome, the result of colonization. So for example, Zulus in South Africa, they learn English in addition to Swahili. And so we also have people who have studied another language in school. Likely most, if not all of you, have taken a language class in the past, whether it was high school, maybe you're taking a language class now at Westmont, or perhaps you know another language because there was a language outside of English that was spoken in your house, in your family growing up. And so the research on bilingual individuals has shown us some interesting information. And it's been found that there are two important predictors of success that are involved in acquiring a second language. So the first one of these is motivation, right? That makes sense. The more motivated you are to learn a language, the more likely you are to actually master that language. And another predictor is the person's attitude towards the people group, the speakers, the native speakers of that language. In one study, the question was how well could English-speaking Canadian high school students learn French? And this study found that the students' attitudes towards French Canadians were actually just as important as their cognitive language learning aptitude. So it wasn't necessarily, it didn't have to do necessarily with, oh, you know, how good are you at learning languages? But also, well, how do you see, what is your perspective? What is your take on people who speak French? Particularly people that speak French in your country, French Canadians. And also, it's been found that, again, doing more English and French studies in Canada, elementary school children who were English-speaking Canadians and then learned French, they actually developed more positive attitudes towards French Canadians than children in the control group who just spoke English. So here we have a sense of the attitude that you have towards the people who speak that language being a really important factor in your ability to learn that language as well. So during the early 1900s, theorists had proposed that bilingualism was something that would produce cognitive deficits. And the idea here was, well, it has to be because the brain, it has to store two linguistic systems at the same time. So really this idea of, well, having to store two different languages, that really takes up a lot of brain real estate. But by the time that the cognitive revolution came around in the 1960s, and we had a better understanding of how the brain stores information, researchers had discovered that people who are bilingual tended to score higher than people who are monolingual on a variety of tasks when they're controlling for certain variables like social class or socioeconomic status. So besides the sort of just given advantage of knowing a second language, bilinguals also have the advantage of being able to acquire more expertise in their first language. And so it seems that learning a second language makes a person more aware of and sensitive to the language structure of their first language. So additionally, bilinguals are more aware that the names that are assigned to concepts, the labels that we name things, are really arbitrary. And this awareness of this just sort of random assignment of sounds to an object or a concept is called metalinguistic knowledge. And in a number of studies that have examined metalinguistics, bilinguals have outscored monolinguals on a number of different measures of this. It's also been found that bilinguals are more sensitive to subtle aspects of language. So they're able, for example, to tell you that the sentence, "the dog meows," is still grammatically correct, even though its semanticity, its meaning, is questionable. But they can tell you that the grammar and the syntax rules still apply. And also, bilinguals perform better than monolinguals on a wide variety of cognitive tasks that are related to intelligence. So for instance, there are these researchers named Bialystok and Martin in 2004 that had preschoolers sort out some cards. And these cards featured either a blue circle, a red circle, a blue square, or a red square. And so first, these kids were asked to sort the cards according to their shape. And then they were asked to sort the cards again, but according to their color this time. And they found that bilingual children were faster to make the switch when they were sorting these cards out according to the new rule. So these bilingual children were able to make the rule switch faster than their monolingual peers. Bilinguals have also been shown to perform better on concept formation tasks, on tests of nonverbal intelligence that require having to reorganize visual information, problem-solving tasks that require them to ignore irrelevant information. So having to problem solve while also not getting distracted by things, and then also on tests of creativity. And then another advantage is that bilingual children have been found to be better able to take another person's perspective. Specifically, English-speaking children whose classes were taught in French were more aware than monolinguals that more information was needed when they were asked to do a task in which they were talking to somebody who was wearing a blindfold. So here, these children were better able to take the perspective of the person they were interacting with who is blindfolded and to use more descriptive language to help the person better understand what was going on. And so we've been talking about a lot of different advantages to being bilingual, and there are actually only really few and minor disadvantages. One of them, I would really say it's not really a disadvantage necessarily, but the pronunciation of speech in both languages that the person speaks might be altered to some degree. So essentially, they have an accent in both languages, which again, I don't really think that's disadvantage. I think that's just more sort of um, a, a fact of life, that just kind of comes along with the territory. And then also, bilinguals may also process language more slowly than monolinguals. So overall, it appears that becoming proficient with more than one language is really beneficial to a number of various brain abilities. So that's not to say that if you only speak one language that you are at any sort of disadvantage or anything like that. But if you've ever been interested in learning a new language, I would encourage you to try it out. The evidence shows that at the very least, it'll be a really good workout for your brain. All right, and that's where we'll stop for today. On Wednesday, we will begin talking about problem solving.